the
Uh,
pop.
so so we'll be discussing this paper called Consistency Preserving Visual Question Answering in Medical Imaging. And this is research that comes from the University of Bern in Switzerland. And these are the contributors. So here's some quick background on this paper. This was presented last year at the McKay conference, which took place in Singapore. I attached the paper, the link to the paper and to the code if anyone's interested in taking a look. And before I begin, I want to introduce what visual question answering models look like, or what they are. These are models which essentially answer a natural language question regarding an image input. So we can consider this black box right here as our model. On inference, we want to feed it this input image of a person with bananas placed on their upper lip. And we want to ask the model a question pertaining to this image, such as, what is the mustache made of? Now, a well-working model should give us an answer that is coherent to both the image and the question. And our answer is bananas, which suffices the coherence criteria. So I know this wasn't a very serious example, but it should be enough to get the point across and have us wondering how something like this could be useful in medical imaging. So an efficient VQA model could potentially aid a doctor in identifying an anomaly in an organ, like in this example. So when asked if a lesion is associated with a mass, an efficient model would aid in the diagnosis. Or it can answer an even more general question, like here, where we have what looks like an image of a torso from the coronal plane, and the model is asked about what it finds to be the most alarming part of this MRI. So its answer is that it is identifies a focal nodular hyperplasia, which happens to be a lesion that sometimes occurs in the liver. So it would be somewhere in this region right here. And so here's one final example. So all we're doing for all of these questions is we're asking the model if it can detect an anomaly. And here in this case, the model notes that there is no variant torsion that's present in the female patient. So due to the lack of large-scale medical data that's available, training these models isn't something that's easy to do. So most of the research that's been geared towards overcoming these data set limitations and also towards building the effective model architectures with the data that we do have. But the main purpose of this paper is to solve a different problem than these. The authors aim to address the issue of consistency in answers from VQA models. So consistency is defined as the ability of a model to answer multiple questions about an image while not contradicting itself. In order to understand consistency a little more, let's take a look at the categories of questions that a VQA model can receive. So we have two categories. One are perception questions. These involve questions that can be answered by identifying or perceiving elements in the image. So this can either be limited to a certain region of the image, or it could be the entire image as a whole. The other category are reasoning questions, and these are questions whose answers can be inferred from the image or region which was identified by the perception question. So in other words, we can assume that the answers to these questions can have some prior knowledge. Next, I want to display a counterexample of consistency, where we have an inconsistent pair of answers given to questions. So we're observing an eyeball right here in this image, and we want to ask a general reasoning question. Is this image healthy? So the model would tell us yes. If we follow up with another question, are there hard exudates here? And we focus on a specific portion of the region of the image, our model would also tell us yes. But there's an issue here. And the issue is that hard exudates are not something that a healthy eyeball would have. So either one of these answers has to be wrong. So this is the type of inconsistency that we want to avoid. There is some related work which kind of attempts to solve this problem. This model called Squint was introduced in 2020, and the way that it works is it considers both question types and reasoning, so the reasoning and the perceptual, and it forms an attention map from the two questions and an attention loss, which encourages the model to get both of these question types right. And this approach is helpful in forming the relations between the two types of questions, but the authors of the paper, which I'm presenting here, claim that it doesn't increase the consistency by too much. But what they do propose is that they can tackle the consistency problem through the use of a loss function that penalizes incorrect perceptual answers when correct reasoning answers are given. So in addition to improving consistency, they also claim that their model achieves a higher accuracy when compared to other current state-of-the-art methods. And the reason for this increased accuracy is that when certain region-specific questions are asked, all other parts of the image are marked as 0, which teaches a model to consider them as irrelevant in the scope of the question. So let's go back to that image of the eyeball and that same question. So we take a whole image and we ask that same question. Are there hard exudates here pointing to a specific region? So the image would mark everything else as 0 and just focus on that region. So this is how the overall training process works. We first take a batch of images from the image set denoted by big I and encode these with a ResNet 101 to get our visual feature space. We take a batch of questions from the big Q set and encode these using a single layer LSTM, so a recurrent neural net, to get our text feature space. These two spaces are then related to one another through an attention module, which results in us getting the attention vector K. Now this vector K is then convolved with the original feature space, visual feature space, and this results in a feature map with attended visual representations. So we then take these attended visual features and concatenate them with the text features so that they are jointly represented, so that these two modalities are jointly represented. And that is denoted by this multimodal fusion block right here, which gets passed into a multi-layer perceptron, which acts as a classifier and gives us our answers in terms of distributions. And so this whole block right here is denoted by this function right here. So let's go ahead and explain the loss functions, of which there are two. So the first function is a cross-entropy loss function, which just gives us an error based on a predicted answer when compared to the ground truth. And the second one is a consistency loss. But before we look at that, let's observe how the consistency relations are formed in the training data set. So the way that this is done is that when we have a reasoning question QI and a perception question QJ, we add this binary relation to let the data know that these two are related. So we know that consistency is the ability of a model to answer multiple questions while not contradicting itself, right? But now that we are well acquainted with perception and reasoning questions, we can define this a little more explicitly. Or rather, we can define the notion of inconsistency, which is when the model infers a reasoning question correctly, but a perception question incorrectly. So I know that we actually saw this earlier, but here's the definition in more concrete terms. So in order to penalize these cases of inconsistency, the model uses two additional cross-entropy losses. So this equation right here on the left considers the correctness of the reasoning answer, and the one on the right, the correctness of the perception. So when we have a high cross-entropy value for the reasoning and a low value for the perception, that's when we want to penalize the model. And the way that this is done is through a hinge loss. So here we want to multiply the loss from the reasoning by the maximum of either 0 and the difference of a threshold parameter and the perception. So where the only constraint here with this gamma parameter is that it has to be greater than 0. And what this means is that if the perception loss is high enough or higher than the threshold, then this will result in a negative difference, making this whole thing 0, meaning that the model doesn't observe enough of an inconsistency to penalize itself over. But if this HJ is low enough, then we will be multiplying the difference of these two by the HI value and enforcing the inconsistency penalization. So now we can wrap up the final loss function, and here's the loss in its totality. So all it really is a minimization of the expectation of the VQA loss plus the minimization of the expectation of the consistency loss. This lambda parameter here controls the relative strength of the consistency loss, since we're multiplying it by the whole thing. So increasing this will theoretically increase the consistency, but at the potential decrease of the overall accuracy, because if this is too high, this term on the right is too high, then it'll negatively affect the one on the left. So here's another image of the model with all of its parts now. So we take a batch of images and a batch of questions. From there, it predicts answers for the questions and answers overall and calculates the two losses, the main loss and the consistency loss. One thing I want to note is that here, these little identifiers, main, sub, and end, are just the types of questions that are asked. So main is synonymous with reasoning questions. Sub, we can consider the same as perception questions. And end refers to independent questions, where in the case that the model gets these questions, it just doesn't apply the consistency loss function. So the experiments that were conducted are on a couple of eye data sets, and they look for the presence of diabetic macular edema. This is a disease that diabetic people are susceptible to, where high blood sugar can damage the blood vessels in their eyes and can result in vision impairment. The data sets used were a combination of the Indian diabetic retinopathy image data set and the E-OFTA data set. And after combining these two, there were a total of 128 images with segmentation of hard exudates, 128 images without hard exudates, and 423 images with the grading for this DME disease. Now, for the question answer pairs, there were 9,779 pairs used for training, 2,380 for validation, and 1,311 for testing. Note that the images here are mutually exclusive to these question answer pairs, meaning that, like, for example, the testing split didn't see any images that were used for training or validation, or vice versa. Okay, so let's look at how these questions are actually asked. First, we look at the reasoning questions, which look for the presence of diabetic macular edema. And the question that we ask is, what is the DME grade? This involves a grading on a 0 to 2 scale, with 0 being a healthy eye where no exudates are present. A score of 1 shows the presence of these masses, but outside of a region for major concern. So while we wouldn't classify this as a healthy eye, it's not necessarily critical, like in a grading of 2, where the patient is at an increased risk for vision impairment. And that's when these exudates are present in the macular region. So in turn, there are 3 different perceptual questions that can be asked about the image. Are there any hard exudates in the image, in the macula, or in the region? So note how these are all slightly different questions, and they they affect the training differently. So for this first example, we're looking at the overall image, meaning that there is no need for these segmentations. But for these two, we're going to apply segmentations because we're asking the model to look at a certain region. And the answers to these questions are either just yes or no. So here are some qualitative examples on how this work performed when compared to others. Here we have the questions that were asked, the type of questions that they are, and the third column is our ground truth answers. This baseline model right here is the same which was covered in the previous slides, but just without the consistency loss. The squint we've already briefly discussed, and then we have our model right here with the consistency. So for this first example, we see that the model is the only one with the accurate answers. The first two get the main question correct, but struggle with answering some of the perception questions, what they struggle with, in other words, is with enforcing consistency. So we can observe the same for this second image right here. So this is the only one that gets everything right and enforces consistency. But for this last image, the model fails in terms of both overall accuracy and consistency. So I think this isn't really explicitly addressed in the paper, but I think that the reason for this failed experiment is that the consistency loss might be contingent on the overall accuracy of the model. So if the main question is incorrect, then the sub-questions will most likely also be wrong. So now that we've seen the quantitative, let's take a look at the qualitative. We're comparing this model with a baseline model without attention to one with attention to the squint. And then there's that model. So the accuracies are measured individually. The answers for reasoning are given by these grade columns. Perception is measured by the whole, the macula, and the region columns. So these are the 3 questions which we covered a couple slides back. And then these are all averaged out to get the overall accuracy. In addition, the authors also designed 2 other metrics, C1, which is a percentage of sub-questions that are answered correctly when the main question is also answered correctly, and C2, which is the percentage of main questions that were answered correctly when all the corresponding sub-questions were answered correctly. So these are just interchanged. Overall, we observe that this paper's work obtains a higher accuracy for all the question types and also on average, in addition to having better consistency scores. So in conclusion, I think the main contribution here was that loss function, which we can use to enforce consistency between the reasoning and perception questions that are related to one another. And in turn, I think this helps with increasing the overall accuracy of the model. These are some strengths that I found with the paper. I think that the consistency loss function is pretty ingenious. I think the use of this Hinch loss designed to penalize the wrong perception answers is something that I can see being incorporated by future works. I also think that this model has somewhat of a robust architecture, and this is shown by the experiments that were conducted, which use varying values of lambdas and gammas hyperparameters. So the tests showed that, yeah, there are some slight changes in performance, especially when you alter the lambda parameter, but it did not completely deteriorate the general performance overall. So if you could see, all these values are all kind of similar, regardless of what the value they change for lambda and gamma, and then same for consistency scores. So now on to some weaknesses. I feel that the experiment portion of the research could have been a little more extensive. There could have been other modalities, like maybe a data set containing the MRIs, like in the example that we saw at the beginning of the presentation, which would have been nice to see for some training and testing to be done on. Additionally, multiple modalities would have given us a more well-rounded picture of the capabilities of the model. And when we only get to gauge the performance from one, like modality, like the eye data sets, then we can start to wonder whether this method would fare well in a more semantically complicated setting. Something else that caught my attention is that this paper was missing out on some very basic metrics, such as precision, recall, and F1 scores. Including these would have been necessarily a complicated ordeal, and once again, it would have given us a better picture of the overall capabilities. So the rating that I would give this is a 2. I feel that the overall lack of experimentation has a lot of room for improvement and maybe seemed a little rushed, but the overarching contribution, which is a consistency loss function, makes me believe that this is a promising addition to researchers creating future VQA models. And as such, I think that it is a good paper. And finally, I'd like to discuss some ideas that I came up with when reading it. So one idea is to replace a LSTM with a transformer encoder. So for this first point, this might not be completely necessary, right? Since the short-term attribute, the short-term memory attribute of the LSTM excels in a task like this, where we're taking sequential questions. But I do think that using a transformer encoder could maybe reduce the computational cost of this whole text encoding operation. Something that also came to me was the potential of expanding the notion of consistency to more than 2 questions at a time. So I'm not exactly sure what the loss function would look like, but it seems to me that this could be feasible. So we only really need to replace the binary hinge with maybe something like a multi-class hinge. This is something that I came up with. I'm not sure if this would work exactly, but something similar I think might work. So I haven't really searched to see if any other MedVQA papers have implemented these with a consistency loss, but it wouldn't surprise me because these seem pretty straightforward. So that marks the end of my presentation. Thank you.